Okay. Ji Shasan, should we continue or should we just start afresh in a new session? आप लोग suggest कर दें. Hello.
जी सर, कंटिन्यू करें सर.
Okay, okay, all right. So let's wait कि कुछ और लोग भी reconnect कर लें. Okay. So now I would start first by telling you why heteroscedasticity is a problem for econometric model. I mean, why should you care? अगर आपके econometric model को कोई issue नहीं है तो ज़ाहिर है फिर तो आपको heteroscedasticity का कोई वो नहीं करना चाहिए. But because it actually brings some problems for your econometric model, that's why you should always take care of this problem. Okay. All right. Okay, so the next thing is, in a sense, why is it a problem? By it, of course, I mean heteroscedasticity. Okay. So why this heteroscedasticity is a problem, right? Or that is, what are the consequences, right?
सर ये स्क्रीन शेयर करें जरा.
Okay, sorry, ये मैं हर दफ़ा भूल जाता हूँ. Thank you for reminding. शाह हसन जो है ना, आपको 1-2 मार्क्स एक्स्ट्रा मिलने चाहिए, ठीक है?
Thank you sir.
Because I usually forget that I should share the screen. तो बाकी participants को तो अच्छा नहीं लगेगा. वैसे I was just joking, ठीक है? I don't want to just. Okay, right. Is it okay now?
Yes sir.
All right. So the important thing is, acha, before I can, why is it a problem, right? So the important thing is that you should know what are the consequences of this problem that we call heteroscedasticity. Before I can tell you the consequences, one thing which you should always remember, in contrast to multicollinearity, where we had discussed that multicollinearity is not an issue of presence or absence, okay? Multicollinearity is always there in your model. It's only a problem of degree, whether it is severe or whether it is not severe. और उसके लिए फिर हमने वो VIF के through determine किया कि is there a serious case of multicollinearity in your model or not. In contrast to that, heteroscedasticity is definitely a problem of presence or absence. यानी आपके मॉडल में या तो heteroscedasticity का issue होगा और या नहीं होगा. If there is no problem of heteroscedasticity, then you should be very happy. You will be the most happiest person on earth if you don't have any problem of multicollinearity, which means you don't need to do anything, right? Or it would be present and you have to then think for a solution. In a short while, we would actually know, okay, how can you know that it is present or absent? इसको फिर हम कहते हैं detection, right? The second thing that you should remember, which is a little bit different from multicollinearity, In case of multicoordinarity, we said that multicoordinarity is an issue only in multiple linear regression model, which means when you have two or more explanatory variables in your model, only then you can think of multicoordinarity, okay? In case of simple regression model, because there is only one explanatory variable x, so there is no issue of multicoordinarity. But in case of heteroscedasticity, irrespective of whether your model contains one explanatory variable or whether it contains many explanatory variables, right? Heteroscedasticity may be there, it may not be there. So it is not dependent on the number of X variables in your model. So these are the two things that you should remember in comparison to multicoordinarity. Okay, I repeat. Number one, heteroscedasticity is definitely the problem of presence or absence. Either is it there or it is not there. And number two, problem of heteroscedasticity would be there if you have one explanatory variable in your model or if you have many explanatory variables in your model. So therefore, it makes sense to talk about presence or absence, while in case of multicoordinarity, it doesn't make that much thing. So what are the consequences? Which means that if heteroscedasticity is there in your model, जो कि अभी मैं आपको बताऊंगा कि how can you know that it is there. But suppose you don't care, या तो आपको पता नहीं है यानी आपने अपने मॉडल को चेक नहीं किया है, और या आपको पता चल गया है but you say I don't care, मैं इस मॉडल के as it is use करना चाहता हूँ. So what would be the consequences? By consequences I mean what would be the price that you would pay. The first consequence that you would have would be the expressions, okay? Maybe I should just do it like this. The consequence number one would be okay, let me write down the first consequence. Sorry, this is the expressions for variances and standard errors of the OLS estimators will be incorrect. This is consequence number one. Okay. The first consequence says that the expressions, which means the formulae for variances and standard errors, right, of the OLS estimators will be incorrect. इसका मतलब ये है कि the standard results for the variance of the OLS estimators and the standard errors that you use in your model for checking the significance of your variables, they are based on the assumption of constant variance. But if heteroscedasticity is there and you still use the same old formulae, it means you're using the wrong formula. And number two, the inferences based on T ratio and F ratio will be invalid. These are the two consequences that you should always remember. अभी मैं आपको मॉडल के केस में इसको एक्सप्लेन करता हूँ कि what we mean by this. Okay, what we mean by this. The first consequence says that the formulae, expressions means the formulae, which will be used for calculating the variance or the standard, because what is standard error? It is simply the square root of variance. So the formulae for variance and ultimately standard errors of the OLS estimators will be incorrect. You will be using the wrong formula for the standard errors. And connected with the first consequence, the inference that you will be using, you will be making, inference means like hypothesis testing conclusion, which are based on T ratio and F ratio, it will become invalid. Like before I can show you the stata output, under the homoscedasticity, right? If the variance of the disturbance term remains constant, right? Then in SLRM, simple linear regression model, right? Y equal to beta naught plus beta 1 x plus u we have the variance of beta 1 hat which we use for making statistical inference regarding the effect of x on y. It is actually given by something like this: sigma square divided by sigma x minus x bar square. This is actually the formula which we use, and the standard error of beta 1 hat, right? The standard error of beta 1 hat is simply then the square root of this variance, which means the square root of this particular variance. And for example, when you are testing the hypothesis H naught beta 1 equal to 0, okay, when you are testing this hypothesis, this is the hypothesis that you use or you test in order to determine the effect of x on y, okay? You use the T ratio beta 1 hat, the coefficient divided by standard error of beta 1 hat, right? This is the standard procedure that you use for testing hypothesis, for making this inference. Inference actually means testing a hypothesis. So in order to determine the effect of x on y, you test this hypothesis, beta 1 equal to 0, and this hypothesis is actually tested through this T ratio. If this T ratio is significant, which means in rule of thumb says if it is more than 2, then in that case you say that this null hypothesis is rejected, and therefore we say that x has a significant effect of x on y. Now, within this expression, you see in the denominator, you are using this standard error, for which the expression is this one. And here, you are assuming a constant variance. When this formula was derived, although we have not gone for the derivation, right? When this formula was derived, it was derived under the assumption of homoscedasticity. When you assume that the variance of disturbance term and ultimately the variance of y is constant given by sigma square, right? यहाँ पे जो मैंने आपको शो किया था ना, this one here. When I said that variance of u or variance of y is actually sigma square, this one, so it is actually used over here in this case. But this is the standard result under homoscedasticity. In case of heteroscedasticity, okay, in case of heteroscedasticity, we have something like this. In case of heteroscedasticity, okay, this is a longer name. Variance of the same beta 1 hat that you saw over here, okay, is something like this. Variance of this beta 1 hat in case of heteroscedasticity is not something that it is equal to summation xi square sigma I square divided by this is something that I should mention here. This is summation xi minus x bar whole square into sigma I square, where sigma I is the changing variance, divided by sigma xi minus x bar square whole square. Okay, the purpose is not to tell you that you should remember this formula, but the purpose is to tell you that under heteroscedasticity, right? Under homoscedasticity, the variance is given by this one. Under heteroscedasticity, the variance is given by this expression, okay? And the standard error of beta 1 hat under heteroscedasticity that you should actually use in your calculation, okay? The standard error would be simply the square root of this, which means the square root of this, Okay. So if there is homoscedasticity, you should use this formula. And it should be used here in the T ratio. But if there is heteroscedasticity, then rather than using this formula, this simplified formula, the theory says that you should actually use this complicated formula. And this is only for the simple regression model. If you have a multiple regression model, then you would have a little bit further expression. So if there is heteroscedasticity and you still use the formula which is actually meant for the constant variance assumption, right? Then this T ratio that you are using for testing this hypothesis, this T ratio, which actually involves a wrong expression for standard error, you are using this one, while actually you should have used this one, right? You should use a T ratio in which beta 1 hat would be as before, but this standard error, this should be actually considered in the denominator over here. So rather than using this one, if you're using this same old formula, which is actually no more suitable, what you will be getting, you will be having a wrong T ratio. So testing a hypothesis on the basis of a wrong T ratio would actually be invalid. That was the reason when I was telling you that because the expression for variances of the OLS estimator or the expression for the standard errors of the OLS estimators will be incorrect, that is the reason that the inferences, the hypothesis testing that you will be making on the basis of T ratio, and also when you will be testing the overall model, the F ratio that you will be using, right? This would be totally wrong. To show you the same thing in Stata, it is something like this. Okay. Like, for example, in this model, heteroscedasticity actually says that if this model is suffering from heteroscedasticity, इसको फिलहाल हमने check नहीं किया है, but just imagine that suppose the model that you have fitted, okay, original model, check कर लेते हैं, this one. Then the standard errors that you have over here, these standard errors are actually based on the assumption of constant variance. Okay, these standard errors जिसको use करके आप ये T ratio calculate करते हैं, and using these T ratio then you compute the P values, and on the basis of these P values you then make conclusion about the effect of a particular X variable on the dependent variable Y, right? जिस तरह यहाँ पे आप ये कह रहे हैं कि the effect of weight on price of the car is significant, and the effect of MPG in this model is not significant, right? So all these T ratios are computed by making use of these standard errors, right? Because in all these cases, this T is actually computed by something like beta I hat divided by standard error of beta I hat. Beta I hat. So this is actually every T ratio here is the ratio of the coefficient, which is beta I hat divided by standard error. So the whole thing is that if these standard errors are computed under the assumption of constant variance, and if the constant variance assumption is no more holding, then what about this T ratio? All these T ratios would be wrong. And any conclusion on the basis of these wrong T ratios would be actually wrong. The same is the case with this F ratio. this F ratio that you are actually using over here, right? This F ratio of 7.48 is the ratio of MS model to the MS residue. This MS residue that you calculate over here, remember this number, which is actually, because you know F is actually the ratio of two mean square. Mean square for model, okay, divided by mean square for residue. Mean square for the residue. So the mean square for model divided by mean square for residue. Now this mean square for residue, which you can see on the screen right now, it is also calculated assuming constant variance. Assuming constant variance. If constant variance assumption is no more holding, it means that the denominator in the F ratio, this is totally wrong. And when this denominator is wrong, it means that this F ratio is wrong. If this F ratio is wrong, any conclusion that you draw about the overall significance of the model is actually invalid, right? So have you got the point? Why we say that statistical inference become invalid? Because you should have used revised formulae, new formulae, right? Under the assumption of heteroscedasticity. But if you ignore that fact, you will be using the expressions for the standard errors and for the calculation of the mean square residue, which are based on the formulae which are no more valid. So agar wo formulae ab valid nahi hai, so any calculation on that would be also invalid. And therefore, any statistical inference that you make about your overall model using the F ratio and about the individual significance using the T ratio, they would become totally invalid. So these are the two important, one is this one, okay, which says that the expression would be incorrect. And the second one is a direct consequence of the first one, because if the expressions are incorrect, what would be the effect? The effect would be that your inferences would be wrong. One thing that you should remember, interestingly, that if heteroscedasticity is there, which I will show you in a minute, kis tarah aapko pata chalega ki heteroscedasticity is there, your estimated model would not be affected, right? So for example, irrespective of whether heteroscedasticity is there or it is not there, okay, this model that you have estimated, model estimation would not be affected, which means you will be able to get the coefficients beta 1 hat, beta 2 hat, beta 3 hat for your model. The model estimation would not be an issue. The problem comes after you estimate the model. यानी इसके बाद जब आप next इस तरफ आते हैं ना, right? When you compute the T ratios, you have to make use of the standard errors. If these standard errors are wrong, these T ratios are wrong, and therefore your whole statistical inference will be wrong. Similarly, if you are testing the overall model, you are using this F ratio. So if the constant variance assumption is no more there, it means that this mean square residue that you compute here in the NOVA table, this would no more be valid. If this is no more valid, because ye F ke denominator mein aata hai na, F is equal to mean square model divided by mean square residue. So if mean square residue is wrong, it means F ratio is wrong. And therefore, not only your conclusion about the overall model would be wrong, but your conclusion about the individual significance would also be wrong. So these are actually the consequences that you see. Now, the next question is, how can you know that your model is suffering from the effects of, or how can you know that heteroscedasticity is present in your model? So let us just quickly do that thing, okay, before we have this time finished. There are two ways of doing that thing. फिलहाल मैं आपको objective way बताऊंगा, although there is a graphical way that you can use, okay. There is a particular statistical test that you can actually use over here. Okay. Detection of heteroscedasticity. One is the graphical approach, and the second one is a statistical test. So statistical test. I will tell you about the graphical approach in the next lecture. Right now, I will tell you about the statistical test. There are two tests which are available. One is what we call the Bpg test. And the second one is what you call the White's test. Bpg stands for Breusch-Pagan-Gottfried test. Okay. B-R-E-U-S-C-H, Breusch, sorry, this is B. Breusch-Pagan-Gottfried. These were three people who actually suggested this test. So in short, we will call it the Bpg test. And the second one is the White's test, right? So let me show you in Stata, and I will tell you the detail in the next lecture. The Bpg test, let me just type a comment. Testing for hetero. Okay. So first, I would just use the Bpg test. This is by far the most simple one. After you fit the model, remember, this is just a post-estimation command. So the model must have been fitted, right? So first fit the model, because we have already fitted the model using the rec command. तो अगर आपने model fit नहीं किया है, तो पहले आप model के fit कर लें. So we have already fitted the model. In order to determine whether this model that we have fitted, whether in this model heteroscedasticity is there, I mean constant variance assumption is there, or non-constant variance situation is there. So simply type HETTEST, het test, het for heteroscedasticity, test for testing. But remember, there will be no gap between het and test. So it should be written in as one word, HETTEST, right? And this is what you get on the screen. The null hypothesis, right, in this test, the null hypothesis is this one, as you can see here, H0, constant variance. So the null hypothesis is that of homoscedasticity. Okay. Homo. Or in short, I will just call it homoscedasticity. And the alternative hypothesis in this test and in any other test of heteroscedasticity is that of heteroscedasticity, which means that if you get an insignificant result, right? If the p-value is less than 0.05, you say, I have got a significant result. So it performs a test using a chi-square statistic, but you have to look at this p-value, right? If this p-value is less than the usual standard 0.05, okay? Which means if you have a significant p-value, right, then your conclusion should be reject H naught. Reject H naught. Otherwise, you should not reject H naught. So what is the result over here? What, on the basis of this p-value, what should be your conclusion? Homoscedasticity होगी या heteroscedasticity? Anyone? G?
Hetero.
Yeah, it indicates heteroscedasticity. देखें, मैंने अभी आपको ये बताया ना. Null hypothesis represents homoscedasticity. Alternative hypothesis represent hetero. वो तो यहाँ पे भी लिखा है ना, H naught constant variance. Constant variance means homoscedasticity. So if H naught represents constant variance, then H1 would automatically represent the opposite of that. So in simple language, we would say that the null hypothesis in the Broish-Pagan test represent homoscedasticity. अगर null hypothesis reject नहीं होता तो हम conclude करेंगे कि there is homoscedasticity. But if null hypothesis is rejected, then we say there is heteroscedasticity. Okay? So therefore, in the given case, because the p-value is less than 0.05, we have a significant p-value. So therefore, we would say that the null hypothesis of constant variance is rejected, and therefore we conclude that in this model is having heteroscedasticity, right? So therefore, you should not use this model as it is. The second model, let me quickly just write down. The second one is white test, right? But you should use only one of them. ये मैं वैसे लिख रहा हूँ, लेकिन ज़रूरी नहीं कि आप दोनों को use करें, ठीक है? So either use the head test, which is the simple, or the white test says, after fitting the model, just type IMTEST, comma, white. This is the command for white test, right? Which is a little bit longer than the Bpg test. So if you just click, right, this is what you get. Again, as you can see here, this is the null hypothesis, homoscedasticity. And this is alternative hypothesis, heteroscedasticity. So just like the Bpg test, null hypothesis says that the variance is constant, homoscedasticity, there is no violation, while alternative hypothesis says that there is heteroscedasticity. And the test gives you a p-value like this. This p-value is clearly smaller than 0.05, okay? Which means, यहाँ पे क्या conclusion होगा आपका? Should we reject H naught or should we not reject H naught? G. Is it significant or is it not significant?
Significant, sir.
Exactly,
Reject.
exactly. So we have the same conclusion. Fortunately, both tests will give you the same result, right? P values different हो सकते हैं